All right, line V1, learning task number 6. We're going to take a look at Autotransformer starters. And Autotransformer starter is just going to be another way that we can go and have a partial voltage start on a motor, which once again is going to go and decrease the amount of inrush current that we are going to go and have in. In its most basic form, an Autotransformer starter is going to go and look like something along these lines. Once again, we're going off of a one-line diagram where I'm going to go and have a start and I'm going to go and have a run position. What is missing off of here is obviously the fact that this is going to have to be connected into a Y type of point, along with 3 other ones, but they're only trying to show us a single line at a time. And under start position, I would go and have a connection that would go and look like this. So I'm going to be going through part of my winding. I'm going to be transforming down in order to go and get my motor value of voltage. And then when I go to a full complete run, I'm going to drop out this start section and I'm going to then go and apply full value of voltage over to my motor windings itself. These are a very, very efficient form of startup. We don't go and have heat that is going to be burnt off in the same way as we do with our impedance type of starters. And we do end up having more starting torque per line amp of current than any other type of reduced voltage starter. What they mean by that is that the amount of current that I'm going to ultimately have on the upstream side, the line current that I'm going to have over here, because I am reducing it to come out to my actual motor during the startup, I'm going to go and see a smaller value that motor is going to go and see, but it's not going to be all delivered. It's coming through from a high to a low, which means that ultimately I'm seeing less current coming through. Watts are still going to be the same, but I'm going to get more starting torque out of it per line amp coming in there. They do have another name of compensator starters, although we don't hear it used as often as what we are going to go and hear just Autotransformer starters. Autotransformers themselves you should be familiar with from your second year. Basically, it's going to be a transformer which shares its 100% winding along with a partial winding, where there's going to be some that is going to be directly transmitted out to a load and some that's going to be brought in over here. I could go and feed in, 600 volts into my 100% taps over here. And then what I would be able to do is I would be able to go and take a smaller amount of voltage off any of these. I'd be able to take 300 volts off over here, or I'd be able to take off 65% of 300, whatever that would be, 80%, etc. And I can go and get a smaller value of volts that's going to go and be out. Some of our currents, if we refer back to Autotransformers, and if I put this here as being a load, let me just quickly do that just so that we're familiar with our current path. So if I've got a load that's going to be connected across here, I'm going to go and have, 2 current paths that are going to go and flow. One of those current paths is going to go and be through like that, where I'm going to have some that's going to be directly transmitted to the load through this set of windings over here. I'm also going to go and have another set of current that is going to go and flow through here, which is going to go and give me flux that's going to link through from the other side. Once again, if you're unfamiliar with your Autotransformers, you shouldn't be. You're in 3rd year. And if you are, you've got your 2nd year materials. Go back and take a look through your Autotransformers and then maybe come back in and take a look at the rest of these. Main advantages that we get is that we're going to go and have reductions in current all the way along. And over here, they show us a motor. They're showing us just once again a line current versus motor current, how that actually looks for us on these. What I'm going to see is I have got transformer laws that are going to be met, which is going to be that my kVA in is going to equal my kVA that is going to be fed back out. So if I'm going to go and reduce a voltage, what I can do, I can take my 600 volts, I can then go and do 600 volts at an 80% tap. So I can literally just go 600 times 0.8, which is going to drop me down to 480 volts over here. So this motor, if it was a single phase motor, would be seeing 480 volts across there. And then I can go and figure out what's my amount of current that I'm going to go and have through there. That's going to be based upon the loads at 480 volts. If this thing gave me 100 amps at 480 volts, I could translate that into kVA. 100 times 480 gets me to 48 kVA. And I would have to have the same amount of kVA coming in. So I can just go and take that same 4,800 and divide it by 600. Now this whole calculation that we're doing over here is a single phase calculation, right? It's pretty obvious. There's only a single phase that's going to be operating. That's why we're not using root 3 inside of any of these calculations. But by the time that we go to a 3-phase one, we are going to go and have some, we will have to go and start applying those root 3s into it. They do give us a calculation inside of the book over here. We should maybe just quickly go over top of that one. Hold on, let me just go and Control A, and we'll just delete all of this so we got room. And basically it talks about that I've got a 600 volt motor. It's going to be this motor over here. It's rated for 600 volts, and it's going to go and draw a full load current of 50 amps, FLA, that I'm going to go and have. And it says when started across the line, I'm going to go and have an inrush of 500% of my full load amperes and a starting torque of 150% of my running value. So that we're just working off that start torque. When using the Autotransformer starter set at the 80% tap, what is going to be my initial starting torque and my initial current in the supply line? Let's first just start by examining what this thing would be if we didn't go and use the reduced voltage. If I didn't use the reduced voltage, and if I had 5 times that, that would mean that I would go and have a 250 amp inrush that this thing would be, right? 5 times 250, or 5 times 50 gets me to 250. That's a phenomenally large amount of current to be conducting in. It is going to give us real fast acceleration, and it's going to give us maximum torque, but we don't necessarily need to have that maximum torque. It says that we're going to go and use an autotransformer set at the 80% tap. So if I have an autotransformer set at the 80% tap, I can go and say that my percent that I have, percent squared, is going to be is going to go on proportional to my torque. It's not equal. I should use that proportional signal for that one. So I can go and take 0.8 and I can go and square it. And if you go and take 8 times 8 is 64. So this becomes a 0.64. 64% of whatever my initial torque is. Well, if we go back to the question, we found out that the initial starting torque of this was 150% torque. So I'm going to go and take 64% of 150. So I go 64, or 0.64 times 150, because that's my startup torque, which is then going to go and calculate out to go and tell me that at the instant of startup, under an 80% reduction, I'm going to be looking at a 96% of my full load torque. This is pretty good, right? It's almost 100%, but I'm seeing that I have got a very much reduced amount of voltage that I'm going to go and have. We found out that if we start this thing up across the line, we had that massive inrush 5 times, right? But if I now go and reduce this thing, what I'm able to do is I'm able to go and use that same percentage, that 80% that I've reduced it to, I can use that on that startup torque. So if I had that 250 amps, I did multiply that by 0.8, which is going to go and tell me that my inrush is going to be 200 amps. 250 versus 200 amps, it's not huge, but it is still significant. That's 50 amps of drop that we are reducing out of our system itself. Because this motor is reduced then through that autotransformer, we also have an additional compounding that's going to go and be on my high side, right? If the motor itself is receiving 200 amps, and if it's going to be operating at 80% voltage is going to be that 480 volts that we're going to have. That 200 amps that we are delivering out to this thing at the 80% voltage is also going to be transformed up through that high side, right? This is the low side over here. The high side is still going to be 600 volts. So what I can do is I can say kVA out, 480 times 200, is going to have to be equal to my kVA in that I'm going to go and have on the high side there. Just go and take your 480 times 200 times root 3. That's going to go and give you your motor kVA, and then take that and divide that by 600 times root 3, and that's going to go and tell you that your line side current coming into this autotransformer is going to be reduced down to 160 amps. In other words, this setup that we have over here, let me just go and erase some of these over here. If I were to go and use this setup on my motor, I will draw it over here just as a one line for this. There's my motor that is attached across the 80%. It's got 480 volts. It has got 200 amps that I'm going to go and have. And we are going to go and have this kVA that has to be matched on this side with 160 amps. So if I take a look at it, 160 amps are going to go and travel through like that. It's going to be this value over here, 160. And then if I take a look at what's the difference between 200 amps and 160, I see that that's going to be a value of 40 amps. Where's that 40 amps come from? Well, that 40 amps is going to be another generated current that is going to be happening through here. It's going to be adding in this value over here. And that's all due to the fact that we're pushing current through here, which is going to flux that core, which is going to cut back in and generate voltage across here and current that we're going to have out. All in all, it's a wonderful thing because now we took this 600 volt motor that initially was starting out at 250 amps as inrush. Now, by staking it onto this autotransformer, we are going to only drop the thing down to 160. The motor still gets 200 amps. It's a fairly significant amount of current there. But by the time that I go through the transformation to the high side, we've dropped this thing down to 160 amps. It's just a significant change that we see dropping down. And we really like this because it makes everything much easier on our electrical system. There's two main connections that we can have. We can either go and have a Y connection for these, or we can go and have a delta connection. And these are drawn in just a little bit of a different manner than you're probably used to, but you'll see that these over here are all labeled 0, that's going to be an XO, or a common point that we are going to go and have. And it's as if I've got a Y type of winding, and we're just tapping off, partially down each of these. That's all that this T1 taps are going to go and be. This other one over here, the open delta, we're only going to go and have 2 windings, which makes an open delta starter even cheaper and easier for us to go and operate. But that open delta starter does have a little bit of an issue in that it can cause imbalances just on the phase voltages on my line side, because I'm going to go and have current that's going to be flowing through here and here and here and here, but I don't so much have current that's going to be traveling across from here, right? This one, if you remember dealing with open deltas, we saw that we had both of those currents adding into these, whereas we've only got a single current that is going to be going up each of those other 2 lines. On small motors, not a big deal, but if it's going to be a really large installation, it can be significant enough to cause disturbances. These autotransformers are also not going to be rated to go and give us continuous duty operation. Continuous duty is, would mean that we're constantly starting. First of all, what we covered in the code earlier tells us that we're not allowed to go and run anything from any of our starting methods permanently. They have to go and automatically go and switch out. And secondly, it's just going to cause overheating. They're designed as undersized because they're going to be only operated for a short amount of time. So they can take that current and then they're going to have sufficient time to go and cool off. Because they are windings, they will often also have either a thermistor, which is going to be a reverse acting temperature sensor, basically. It drops its resistance as the temperature goes up that we're going to bury inside of them, or some other type of heat sensitive element that we can couple to external protection on those transformers. Okay, let's talk about the very first one that we have. The first connection that we're going to go through. The first connection we're going to cover is going to go and be an open transition connection that we are going to have. I'm just going to see if I can open that one up. Just make that one a little bit larger over here. So you can see what's going on. And then we've got a control circuit that is going to go and be associated with it. I put both of these together onto the same drawing because it just kind of makes more sense for us to see both at the same time. You'll note that we've got a couple of components that we are familiar with. We have got time delays over here. One of these is normally closed and time to open. The other one is normally open and time to close. But you'll note that both of them are going to be fired by the same one. This one is going to pop open. This one is going to go and pop close. But for a brief second, while this one is opening and while this one's closing, neither one of these is going to be closed. But it's going to be so fast, we're hardly going to notice it, but it is going to be an open transition as a result of this. Looking at our system that we have over here, if we carry our power through, we can see that we would carry power through up to there on our control circuit. And if I were to go and carry power through on my main circuit, I would see that I would have power carried through up to here. The instant that I go and press start, that start is going to go and close in, which is going to go and energize TR, which is going to go and seal that in. So the instant that we go and press start, we carry through to TR, out through our overloads. We've got the temperature sensor that's going to be inside of our autotransformers. And we see that that's going to go and seal in. These are instantaneous contacts that are tied to this timing relay. I also see that I've got a normally closed section over here, our normally closed contact, and a normally open. The normally open is going to stop the current. The normally closed is going to pass it through to my starting contactor. So I'm going to go and close any S's that I'm going to go and have, which is going to be this one, and this one, this one, and this one over here. When I go and close those, we have now gone and set up complete paths for current flow. If I go and highlight those out, we should see that this is going to go through to there. We should see that this is going to go through there, and we should see that this is going to go through to there. And from there, we can go and pass on down to our actual motors through here. Actually, let me just redo that because those motor connections need to be differentiated. This one here goes over there. It's not a dot on that line. It's just crossing over. This motor is going to be fed through here like that off of these. So our motors are going to go and get a reduced, an 80% reduced voltage that we are going to go and start this thing out with. In the meantime, so we just accomplished all of that action. This timer over here, when we powered it up, it's an on delay, so it's doing its timing action. At the end of its timing action, it is going to go and close this one while simultaneously opening this one over here. And so for a brief second, while that one is opening and this one is closing, we're going to go and lose all contactors and all paths of current to the load. It's an open type of transition, which means that we're going to be coasting on our motor just for a brief second. And then, because it's in the middle of process changing, this is all happening across milliseconds, this is going to go and close. And now we're going to be at our R, which means that all of the R contacts over here are going to go and close. And we can see that we're carrying power directly through to the actual load itself, to the motor that we have got attached to this. It's an open transition type of autotransformer. What type of autotransformer is this? Well, this is got two windings across it, and we see that we've got the two windings connected directly up to one of the lines. There's no start point because it's connected onto that line. What we're looking at is we are looking at an open delta autotransformer. Really, if I were to go and take a look at my components that I had inside of there, this is what we would see. You have got the start and the run. This would be an S, this would be an R. We've got two normally opens like that. I'm going to go and have two more normally opens over here that are going to be the S, the start ones. And then I'm going to go and have a set of R's that are going to be going across like this, run ones that are going to be going across like that. So if I were to go through, my sequence, I'm not going to go through the timing sequence, but if I were to go and take a look at it, at the instant of startup, what I would have is I would have closure on all of the S's here, which would mean that I would be able to go and flow line current through like that, and line current through like that. And when that happens, that's going to go and energize these over here, which would mean that I would also be able to go and take off current that's going to be coming through here on the 80% tap. Take off current over here on the 80% and take off over here. The actual delta that my motor is operating over top of is circumscribed by that triangle that we are going to go and have over there. That's during start. Then our contacts are going to go and close, just like we saw in the other one there. And when they go and close, my contacts are going to go and change state. When they change state, all of my S's open up like this. So now I'm going to be open out to all of my loads over here. I'm not going to have any complete connection. And then I'm going to go and close in on these ones over here on my R's. And that's going to allow me to now go and pass current directly through. Oops, sorry, that one's going to go through. Directly through and down to my motor itself. This, what I've just drawn over here with these S's and R's, is the exact same thing as what we have over here. It is an open transition, which means we do have to be careful about any time that we're running it, that we do not let this thing take a long time to go in transition. We're going to go and see a little bit of a torque dip as it is changing over. Okay, let's go and take a look at the next one, which is going to be my closed transition autotransformer starter. All right, so this is looking at the autotransformer starter, the Y, and this is going to be a closed transition one, which means we're never going to go and see a drop in the amount of torque that we're going to be delivering out to our loads, which is a very good thing once again. And we are also going to go and see a more balanced amount of current that we are going to go and take out. As a result, we're also going to go and have a more balanced value of voltage that we are going to get off of these two. One of the fun facts about this one is that allegedly it is called the Korndorfer connection in honor of its inventor. I've never actually fact-checked that one. It's been in this binders for for as long as I can remember, since the 1990s at least. Who knows if it's actually, called the Korndorfer or not. I sometimes suspect that some of the stuff that's inside of here, somebody just put it in there to see if anybody was fact-checking. But maybe that's something for you guys to do. Check it out, see if it's actually called the Korndorfer connection. That being said, how does this one go and operate? Well, this one over here is going to go and have a set of timed contacts. Once again, we see we got a timing relay that is going to go and have two associated contacts with it. One of these which is going to go and be normally open, timed to close. The other one which is going to be normally closed and timed to open. We should also note that the same timing relay that we have here with timed connections also does have one non-timed connection. This one over here, which is going to be an instantaneous one. Lots of our relays, our timed relays, do have the option to have some instantaneous that are just going to follow the coil application, and others that are going to go and be timed the way that we see these other ones down here. Let's follow through our action. Once again, we're just going to start by highlighting what we have got for power and where this is going to go and break down. So we'll start just by erasing all of that. Let's take a look at our power circuit. Our power circuit over here, we see that the power circuit is initially going to go and only carry power through up into there. And on our control circuit, we go through the normally closed, up to the start switch, and up to that switch, or up to that ceiling contact over there. At the instant that we go and close our start, we're then going to go and apply power the rest of the way through over to here. As soon as we apply power to the timing relay coil, we are going to have the instantaneous operation of this over here, which is going to go and seal in, and at the same time we are going to go and have current that is going to go and pass down through here, because this is normally closed, down to each of these contacts that we see over here. Then it's going to go and hit this one, which is also normally closed. It's going to be able to go and pass through that, which is going to go and power up our 1S coil. And once it powers up our 1S coil is then going to go and close and power up our 2S coil. So the instant it hits the 1S is going to fire this closed, which is then going to go and close the 2S coil, which is then going to go and seal itself in like this. What does that do on our starter? Well, let's start by following these through in the order that they closed. The first one that closed was going to go and be the 1S. We saw that the 1S closed first. That's this one here. That 1S closure is simply just going to go and create a Y type of connection. It closes in the coils of all of these over here. We saw that the 1S, when it closed in the 2S as well. And so as soon as we've closed in the 2S over here, that is going to go and apply power now all the way through down to this Y point. So we see that the starting contactors over here provide power down to that Y point. And then we see that as soon as we go and provide that power down to the Y point, that we can then go and tap off from here and feed out to my individual motor leads over here. So we're going to go and have power that's going to be fed through to my motor itself. Next thing that is going to go and happen inside of here, so this is going to start up my motor right now. My motor is starting on my 65% tap at this point. Next thing that's going to go and happen is that this thing is going to finish its timing. So right now it's timing. That's the way we started this thing out at. And the very first thing that it is going to go and do is it is going to once it goes and operates, it's going to go and operate both of these. First thing it's going to do is it's going to start opening this one up over here. And as it opens that one up, it is going to depower 1S. So for a split second over here, as this one opens up, we're going to go and depower 1S, which means that we are going to go and lose all of these over here. There is still going to go and be a path for current through to my load. Because right now with 1S gone, we see that now we can just carry current directly through this top section of the winding over here, which is going to be in series with the motor. But we're able to go and carry that through out to the motor. So we see that this one here has opened up. As that one opened up, it depowered the 1S, which is going to go and depower that set of contacts there. Sorry, 2S is still there. That line just disappeared because it was attached. And I see that at the same time as this is opening up and dropping out the 1S, that we are going to be closing this one over here. And this one over here, once we have closed it, it is going to be able to pass current through the 1S. Note that these ones are interlocked. This 1S over here, meaning that this one has to happen first before we are going to be able to go and send power through to this R1. So R1 now is able to go and close. So we'll just close that R. When I go and close the R over here, that R is also going to go and operate this normally closed, and it's going to make that normally closed go open over here. And when that happens, it's going to go and open this setup down here. It's basically going to go and depower everything that was down below here. At that point, is going to go and lose power, which means that all of this 2S that we have up top here, those are all going to go and lose power, but that's all right because we've already got this R path closed and we have got current that is traveling through to the motor itself. It's a completely closed connection going through that is going to go and always, always, always maintain my flux at the motor. We never once have where the motor itself is going to go and lose power to it, so we don't get that little bit of a torque dip or any type of a line disturbance off of it. Really cool set of auto transformers. I mean, really, when you take a look at both of these, either the Y type of connection or the delta type of connection that we had off of these, both of them are highly useful for being able to go and reduce my value of voltage that I'm going to go and have out to my motor when I utilize them, as well as reduce the total amount of current that I'm going to go and have in. We'll do one more calculation over here since we're at this point. We're going to go and start with a, we'll go with a 600 volt motor for this one, or sorry, with a 600 volt system. If I have got a 600 volt system, that would mean that I'm also going to go and have a motor that's rated for 600 volts. That's what we would have over here as well. My motor that's going to be rated for that 600 volts. When I'm looking at this connection over here, my open delta connection, whatever tap I'm at on those transformers, going from the 0 up, whatever tap is going to be the percentage of voltage that I'm going to go and have across there. So if I have got a 65% tap, right now I would get 65% of that 600 volts. So we'll just quickly pull that one up on 2 seconds. Let's pull this calculator up here. 0.65 times 600, which would mean that I would be starting this thing up at 390 volts that I would go and have initially to start this motor up. So we'll just quickly ixnay that right now. I will say that this motor would be starting at 390 volts, and then when I complete my connection and I take out the actual auto transformer and I go to my full line running, then it would go to 600. So it starts at 390 and then runs at 600 if I'm using 65% taps. If I have got this one over here, I'm going to go and have 600 volts, but when I make that connection, remember that it's connecting those into a Y. So if I'm using the same 600 volt system, but I'm using my 65% taps, now I'm taking 65% of this winding, this 347 volt winding. So I'm going to go and have 347 times 0.65. Which gets me up to a value of 225 volts that I'm going to go and have. So right now I'm going to be at 225 volts there, but remember that this is 225 volts that's still connected as a Y as well, and that 225 would be a phase value of voltage, which means that we should be able to get a line to line by taking that phase value and just multiplying by root 3. So let's do that. So take this times root 3 over here, which gets us up to a value of 390 volts. So I see that on this one as well, because now I'm going with that line to line, and that's really what this motor is connected. Take a look, the motor is connected across from the line to the line. We see that we would be at 390 volts starting, and then kicking that up to the 600 volts when we make that transition. So it makes no difference whether we're doing the open delta or the open Y at 65% is going to be a 65% of voltage. 80% would be an 80% of voltage. It just gives us a lowered value of voltage, which means that we can start out with a much, much reduced value of current on our high side. kVA in is equal to kVA out. All right, that's that.